Hello students, welcome to aimsindia online classes. This is a chemistry session. Here we are discussing about chapter periodic classification. In this session, we are going to see about ionization energy and trending of ionization energy in the groups and periods of modern periodic table. How it is changing from element to element in the periodic table, we are going to see. What is the meaning of this ionization potential and its trending, we are going to see now. Okay. The ionization energy or ionization potential of an element is defined as the minimum amount of energy required to remove an electron from the outermost orbit of an isolated neutral gaseous atom to make it unipositive ion. So this is called ionization potential. Suppose there is an atom. If certain amount of energy is supplied onto this atom, then it ejects an electron from its outermost orbit by absorbing that energy. There, the minimum amount of energy required by that atom to eject this electron in the outermost orbit, and hence it becomes positive ion. So that energy required by that atom is called ionization energy. It can be defined as the minimum amount of energy required to remove an electron from the outermost orbit of an isolated gaseous neutral atom. So this is the definition. To say simply, the amount of energy required to remove an electron from the atom. Energy required to remove the electron. But in which condition the atom should be first? It should be separated from the remaining all atoms, because for the separation of these atoms into individual atoms also certain amount of energy will be utilized. So first it should be separated into individual atoms, and that atom should be converted into gaseous state. In that state only electron can be removed from that atom. So first atom should be separated from the remaining all, that is we say isolation. That's why we use this word isolated. And a gaseous, that atom should be converted first into gaseous state. Even though it is a solid or liquid, first it should be converted into gaseous state, and then it should be in the neutral state. So in these conditions, the energy required by that atom for the removal of an electron from its outermost orbit is called ionization energy. Okay, as we're telling, this is the energy required by an atom. Its units will be whatever the units we say for energy, those will be here units of ionization energy, like electron volts, kilojoules, or kilocalories. These all we can say as the units of ionization energy. But we take in terms of atoms which are very micro particles. So by in certain quantity we take like electron volts per atom, kilojoules per mole, kilocalories per mole. In this way we take the units of ionization energy. It can be expressed mathematically like this. Suppose X is an isolated neutral gaseous atom of an element. Then if we supply certain amount of energy, then that will eject an electron from its outermost orbit. Then the energy absorbed by that atom in that condition is called ionization energy or ionization potential. Then the atom will be converted into positive ion or cation. Okay. There, the minimum amount of energy required to remove an electron from the isolated gaseous neutral atom is also called as first ionization potential, because we are removing the first electron from the atom. The second ionization potential is similarly is defined as the amount of energy required to remove an electron from the outermost shell of an unipositive charged gaseous ion. Means already if it is lost one electron, then the atom forms a unipositive ion, we know. If we want to remove an electron from that unipositive ion, then the amount of energy required by that element is called second ionization potential or second ionization energy. See here, an element X already lost one electron and formed here X plus ion. From that, if we want to remove an electron, then that amount of energy required is called second ionization potential or second ionization energy of that element, and hence the element becomes dipositive ion. Okay. For example, if you see sodium, for the removal of first electron from sodium, it requires 495.8 kilojoules per mole. This much amount of energy required to remove an electron from the 1 mole of sodium atoms. Okay, that we say as first ionization potential of sodium. Then from this sodium plus ion formed thus, to remove the second electron, it requires some more amount of energy that we say as a second ionization potential of sodium. This energy required by the sodium for the removal of second electron. Okay, this we say as second IP or second ionization potential of sodium. Similarly, we can define the third and fourth ionization energies of ionization energies or ionization potentials of an element. If the first ionization energy is considered as IP1 and the second as IP2 and so on, then we can relate these all as IP1 is less than that of IP2 and it is less than that of IP3 and so on. Theoretically, an atom can have as many ionization potentials as there are electrons in it. But if it practically it may not be possible, but theoretically you can say how many electrons are there in an atom, those many ionization potentials we can define. Okay, and here the relation between these all is IP1 is less than, IP2 is less than, IP3 is less than, and so on. Because IP1 means what we are telling, the amount of energy required to remove an electron from the neutral atom, and IP2 means the amount of energy required to remove a second electron or an electron from the unipositive ion, means that atom already lost one electron, means it will be having greater nuclear charge. Number of electrons will be less than the number of protons in the nucleus. Hence, nuclear charge will be more on the remaining electrons. So the removal of second electron becomes a little difficult from that unipositive ion and hence requires greater amount of energy. That's why we say second ionization potential is always greater than first ionization potential, and third ionization potential is always greater than second ionization potential, and so on. Okay. First, second, third, and fourth ionization energies are mentioned here to explain us clearly. For example, first, second, third, and fourth IP values of magnesium and aluminium are mentioned here. Let us see in kilojoules per mole they have mentioned. See, for magnesium and aluminium, if you observe, first ionization potential is smaller than second, and second is smaller than third, and third is smaller than fourth, and so on they will be. Why? Because if you consider aluminium, so if you remove an electron from its outermost shell, we know its outermost shell is having 3 electrons. If you remove one electron, it will be with totally 12, 13 units positive charge. Okay, after the removal of electrons, what happens? The number of electrons becomes only 12 because it lost one electron. But the nuclear charge will be remained as 13 units only, isn't it? Means nuclear charge is greater than number of electrons or negative charge. So as nuclear charge is greater, this will hold the remaining electrons very tightly. That is why the removal of second electron requires more energy. So this is a second ionization potential of aluminium. So after the removal of second electron, what happens? Number of electrons becomes now only 11, whereas positive charge remained as it is, that is 13 units, isn't it? Now, this nuclear charge is much greater on the remaining 11 electrons. So the removal of third electrons becomes much difficult. So it requires more and more energy. That's why the third ionization potential is much greater than that of second, if you observe, isn't it? So if you remove the third electron also, then the number of electrons becomes only 10. But nuclear charge is being maintained as it is, that is 13 units. So nuclear force of attraction on the remaining 10 electrons, which will be much more. It will hold the remaining electrons very tightly. So the removal of fourth electrons becomes much more difficult, and hence it requires more and more energy. So we say IP4 is much greater. So in this way, for any element, IP values gradually increase from IP1 to IP2, IP2 to IP3 and so on, because nuclear charge increases as we remove electrons from them. Got it? And one more we can observe here, after the removal of 3 electrons consecutively from the aluminum, it attains nearest noble gas configuration. That is, it attains neon configuration. That is why it will be more stable after the removal of 3 electrons. So abnormally IP4 value is increased here. See, it is increased gradually till IP3, but for IP4 the IP4 energy value is much more greater than IP3, because after removal of 3 electrons, aluminum is attaining stable configuration. So the removal of fourth electron is much difficult. So it requires more amount of energy. In the case of magnesium, the third IP value is much more greater. After the removal of 2 electrons, what happens? Magnesium attains stable configuration of neon. So the third electron removal becomes much more difficult. So it is having IP3 value more greater, isn't it? Okay. Next. This consecutive EISD is explained here. The successive increase in the values of ionization potentials is due to the increase in the effective nuclear charge from the neutral atom to respective ions. As they are becoming ions by loss of electrons, nuclear charge is being increased. So the remaining electrons are held tightly. The removal of electrons becomes difficult and requires more and more energy. Right? So variation of this ionization potential in the periodic table. This ionization energy or ionization potential shows periodicity. That means it varies in the respective way as we move through the periodic table. That means from top to bottom in a group or from left to right in the period. So this shows certain variation. That shows a certain periodicity. Let us see how it is being varied in the groups and periods. Let us see first in a period. In general, to say ionization energy in a period gradually it increases because size of the atoms decreases. If the size decreases, nuclear force of attraction on the electrons increases and hence ionization potential increases. So this is to say in general based upon the size. In a group in a period from left to right, ionization energy increases. But in fact, from left to right, ionization energy do not follow any regular trend. Let us see why it is so. For example, if you see first period, in the first period, ionization energy increases from hydrogen to helium. Why? Because the helium is attaining stable electronic configuration, means it is attaining noble configuration, duplet configuration, that is 1s2, isn't it? So because of that, helium will be more stable and hence ionization energy is much greater for that. So hydrogen to helium, it gradually increased. So generalized the point it is accepted in the first period. Let us see second period elements. In second period, ionization energy increases from lithium to beryllium. So as the size decreasing from lithium to beryllium, ionization energy increased. But by coming to boron, it decreased again than beryllium. Because if you observe the configurations of these two, beryllium is having paired electrons in its 2s2 configuration, isn't it? We see for beryllium, atomic number is 4. If you say configuration 1s2, 2s2. So S2 orbital is completely filled here. Removal of electrons from this completely filled orbital is a little difficult. Whereas if you see boron, atomic number is 5, and if you read configuration for its 1s2, 2s2, 2p1, isn't it? So it has single electron in the p orbital. Removal of single electron is somewhat easier than the paired electron. Pairing should be disturbed first. So removal of single electron is easier than removal of paired electron. That is why boron is having lower ionization energy than beryllium. But in general, what we say, the size decreasing from beryllium to boron, so it ionization potential also might be increased, but it is not happening here because of some other factor, that is ionization energy or configuration. Beryllium has paired electrons in its s subshell, so the removal of this paired electron is a little difficult than the single electron in case of boron. Okay, that is why from beryllium to boron it decreases, and then again it gradually increases till nitrogen because size decreasing. So after nitrogen again it decreases to oxygen, because here nitrogen is having greater than the expected. That is because of its special configuration. We call that half filled configuration, isn't it? Atomic number of nitrogen is 7. If you see its configuration, 1s2, 2s2, 2p3. So in the p subshell there are 3 electrons. So the 3 orbitals are occupied with a single electron. So in this way it is having half filled configuration. It's a 2p subshell. By the half-filled or completely filled outermost subshells, elements they will attain extra stability. Because of this, nitrogen is being more stable. The removal of electron from this configuration requires more energy than the expected. That is why nitrogen is having greater ionization energy than oxygen. That is why it is decreased from nitrogen to oxygen. Again, it gradually increases till the noble gas neon. In this way, it is not following any regular trend as expected. In general, what we say, as in a period from left to right, atomic size decreasing, ionization energy should be increased in the gradual way. But because of some special configurations, this is being uh, not following any regular trend. Got it? Now let us see in a group, how does it vary? The ionization energy decreases from top to bottom in a group. This is because as we go from top to bottom in a group, the size of the atoms gradually increases, and hence the attractive power of the nucleus on the outermost electron decreases. Therefore, it is easy to remove the electron, and hence the ionization potential decreases. For example, if you see the first column or first group elements are mentioned here with their ionization energies. We know from lithium to cesium, lithium, sodium, potassium, rubidium, cesium, these are first group elements. We call them alkali metals, isn't it? In this group, from lithium to cesium, size gradually increases. As the size increases, nuclear force of attraction on the outer electrons decreases, and hence those electrons can be removed easily. That is, they requiring less amount of energy. Thus, we can say in a group from top to bottom, ionization energy decreases because size increasing. Okay, this is about variation of atomic size, ionization energy. Ionization energy in a group from top to bottom decreases, whereas in a period, in general, to say in a period from left to right, ionization energy increases because size decreasing. But in fact, in periods, it is not following any regular trend because of some special electronic configurations and some other effects. Okay, that's about ionization energy. Now let us see the factors affecting the magnitude of ionization energy. We told here in a period from left to right, ionization energy is not following any regular trend. We told here one of the factors as electron configuration. There are some other factors also which are affecting it. Let us see those factors which are affecting the magnitude of ionization potential. First among them, nuclear charge. As the nuclear charge increases, ionization potential also increases. This is due to the increase in the attractive power of the nucleus over the outermost electrons. So if nucleus attracts the outermost electrons with the greater force, the removal of those electrons becomes difficult and hence ionization potential will be greater for those. So we can summarize this as, if the nuclear charge is greater, ionization potential also will be greater. Next factor, atomic size. When the size of the atom is very large, then electrons of that outermost orbit bound to the nucleus with the weaker attractive forces. Such an element will be readily removed. Such an electron can be removed readily from that atom. Therefore, the value of ionization potential will be low. So, what we can summarize how this atomic size related to ionization potential. The atoms with the greater size will have lower ionization potential. In the reverse way, the atoms with the smallest size will have greater ionization potential. Why? Because in the greater sized atoms, nuclear force of attraction on the outermost electrons will be less, and hence those electrons can be removed easily. Okay. In that way, atomic size is, or ionization potential is, inversely proportional to size of the atoms. One more factor, completely filled and half filled orbitals or completely filled or out half filled electronic configurations. According to Hund's rule, atoms having half filled or completely filled orbitals in their outermost shells, they attain some extra stability and hence more energy needed to remove an electron from their outermost orbits. The ionization potentials of such atoms are therefore relatively higher than they expected from their position in the periodic table. So, the elements with completely filled or half filled electronic configurations, they attain some extra stability. That is why their ionization potentials are being greater than they expected based upon their positions in the periodic table. Let us see some examples here. For example, IP values of noble gas are extremely high. Actually, they are at the right side of the periodic table. As per the trending, if you say from left to right, atomic size decreasing, so ionization potential increases. So they should have the greater ionization potentials. That is being happened, and even they are having the greater ionization potentials than they expected because of this completely filled configurations. The elements which are having completely filled electron configurations, they will be more stable. Removal of electrons from them is much difficult. Hence, they have IP values greater. And one more you can see, IP value of nitrogen is more than the expected because nitrogen has half-filled electronic configuration. In the 2p subshell in the outermost shell, it has half-filled orbitals 2px1, 2py1, 2pz1. So because of this half-filled configuration, it attains some extra stability. Hence, removal of electron becomes difficult. It requires more energy. Okay. So half-filled configuration or completely filled configuration also affecting this ionization potential. Next, inert pair effect. That is, what is this? It is a tendency of the outermost electrons to remain unionized or unshared in compounds of post-transition metals. Post-transition metals means the elements which are positioned after the transition metals in the periodic table. That means in the P block. The term inert pair was first proposed by Neville Sedgwick. For example, in group 13, if you see, this is a first group after the transition elements, isn't it? So third A group we call it, that is aluminium, gallium, indium and thallium. For these elements, the oxidation state +1 is more stable and the oxidation state +3 is rarely seen in their compounds. For example, if you see the +1 oxidation state of thallium is more stable. Thallium is a heavier element among these all. And thallium +3 ion compounds are comparatively rare. The same stability trend is noted in the groups 14, 15 and 16 also. So even though they are having 3 valence electrons, these 13th group elements, if you say thallium, its configuration will be Ns2, Np1. This is a generalized electronic configuration of third period elements. Okay, but here instead of losing these 3 electrons, they are interested in losing only one electron, and hence they are forming +1 ions in their compounds mostly. So they don't lose these two electrons because these are paired electrons. So the removal of the disturbance of these paired electrons requires certain amount of energy, and hence they will be exhibiting all mostly +1 oxygen state instead of +3. Okay, this is because of the paired electrons. This effect is called inert pair effect. So this same tendency is shown in the fourth group, fifth group, and sixth group elements also, and it is mostly shown by the heavier elements which are at the bottom of these groups. Okay, these elements will lose only the electrons which are not paired only. They won't show interest in show removal of these paired electrons. This we call as inert pair effect. Okay. Next, the shielding effect. The electrons of inner orbits repel the electrons of the outermost orbit, due to which the attraction of the nucleus towards the electrons of the outermost orbit decreases. This is known as shielding effect. Suppose it is an atom. Its nucleus is here. These are the inner electrons, and these are the electrons present in the outermost orbit. These inner electrons repel these outer electrons present in the outermost shell. So these electrons move a little away from the nucleus. Hence, nuclear force of attraction on these outermost electrons will be less. Because of this, these electrons can be removed easily and ionization potential will be less. So this is because of the shielding of these inner electrons. Shielding effect of these inner electrons on the outermost electrons. So these are acting as a shield to the outermost electrons, by which nuclear force of attraction on these outer electrons decreasing. This is called shielding effect. Due to this shielding effect, atomic size increases and the value of ionization potential decreases. If these electrons are not there, what happens? The nuclear force of attraction on these electrons will be high, so they will be held tightly, size decreases. But because of these inner electrons, nuclear force of attraction on these outer electrons is being less. These are shielding at the middle. So nuclear force of attraction is being less, and these electrons are moving a little away from the nucleus, so size increases. We know if size increases, ionization potential decreases. So as we move down a group, the number of inner shells increases, and hence ionization potential tends to decrease. We know in a group from element to element, a new shell is being added. So the number of shells being increased. As the number of shells increases, shielding effect increases. Isn't it? Let us see. The second group elements are mentioned here. Beryllium, magnesium, calcium, strontium, barium, and radium, if you see. Now, for beryllium, the configuration can be shown like this. It has only one inner shell, isn't it? First shell only. In the second shell, there are two electrons. So the shielding effect will be somewhat less here. If you see for magnesium, there are totally three shells, isn't it? The two electrons are there in the outermost shell. In between the nucleus and these outermost two electrons, there are two shells. So shielding effect will be a little greater than that of beryllium. If you see for calcium, there will be three inner shells. If you see for barium, there will be five inner shells. So as the number of inner shells increasing, the distance between the outer electrons and the nucleus increases, and these will shield these outermost electrons from the nuclear force of attraction, and hence nuclear force of attraction on the outermost electrons decreases, and hence ionization energy also decreases. So this is a effect of shielding effect. As number of inner shells increases, shielding effect increases, and hence ionization energy decreases. Okay. Let us see a solved example based upon the ionization potentials of the elements. Say which of the following should be the order of the increasing values of second IP values of carbon, nitrogen, oxygen, and fluorine. So these we know there is some relation between these elements. These four elements are in the same period, isn't it? Now they're asking to find the increasing order or decreasing order of second IP values. Second IP means the energy required to remove the outermost electron of unipositive ion, means they already lost one electron. Now let us see that. Second ionization potential means removal of electron from unipositive ion or a cation. See here, for carbon, this will be the configuration after the removal of electron, and for nitrogen it is. We see for the remaining two elements also. Now if you observe these configurations of unipositive ions, this oxygen is attained a stable configuration of nitrogen, isn't it? It attained here half-filled configuration. Now this should have the greatest second ionization potential among these four. So it should be at the last. Now all the options it is given at last. Now if you observe the remaining all, they do not have any stability configurations. Normal configurations are there. So these will be in increasing order of their nuclear charges. We know fluorine is having the greater nuclear charge than nitrogen, and at least for carbon. Now carbon, nitrogen, fluorine, and at last oxygen should be there. In which option it is mentioned? So I think it is here in this fourth option, isn't it? Carbon, nitrogen, fluorine, and oxygen. This is a increasing order of their second IP values of these elements. So we have to understand here, second IP means the amount of energy required to remove an electron from the unipositive ion. That means ion already formed by the removal of one electron. Then if you observe their electronic configurations, we can understand the order of those. Okay. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.